folks, so we'll continue. So yeah, let's see some examples. So let's look at this little derivative here. Now we're going to differentiate with respect to x. So I'm going to keep doing this thing where we kind of really show where the constants are. Mostly the constants that are multiplying. So, well, here there's not so much because it's just maybe the constant. Why am I writing it like that? It's just the constant y here. Now, why is y constant? Because we're differentiating with respect to x partially. So y is kept constant times x squared. Now, the 3 we could call a constant if we wanted, but we're not going to do that, as we'll see why in a moment. And the minus 2y, while it is a constant, it isn't multiplying something, so I won't be painting that red. 3x times sine of x minus 2y. Okay, so off we go. The partial derivative of z with respect to x. So I have a sum of two terms, yx squared plus this other yoke, and to differentiate them, I do term by term, fixing constants. So the constant in the first one is y, fix that, and the derivative of x squared is 2x. Now for the second thing, it's two things multiplied together. And therefore I'm going to use the product rule. So the product rule says the derivative of a product is the first thing by the derivative of the second thing plus the second thing by the derivative of the first thing. So we do plus the first thing. Okay, now the derivative sine of x minus 2y isn't as simple, although it is here actually, as simple as cos of x minus 2y. But if we were differentiating with respect to y, it wouldn't be that simple. So we'll just show that it ends up being as simple as we think. The derivative of sine of x is cos of x, but this is sine of something a bit more complicated. So we have to use the chain rule. So the chain rule says differentiate the outside function. The outside function here is sine of x, and the derivative of sine of x, as we said, is cos of x. Now the chain rule says evaluate that at the inside. So evaluate at x minus 2y, and now multiply by the derivative of what's inside. But here it must be the derivative with respect to x. So we're going to differentiate x minus 2y. And I could have actually painted the 2y being red now that I think about it. Okay, so we're differentiating, multiplying by the derivative of what's inside. Now what's the derivative of x with respect to x is 1. And what's the derivative of minus 2y with respect to x? Well, if y is constant, so is minus 2y, so this is just minus 0. And you notice here with the chain rule, we just multiply by 1. So the derivative actually was as simple as cos of x minus 2y. So that's the first thing by the derivative of the second thing, plus the second thing, which is sine of x minus 2y, times the derivative of the first thing. Now you can just write down 3, but I'm going to go a bit slower. I'm going to fix the constant 3. So this is maybe where we could again, we could again use the color. Fix the constant 3, and the derivative of x with respect to x is 1. So we can tidy this up, y by 2 by x. Now y, 2 and x are all numbers. You can multiply them together whatever order you want. For example, 2xy. And then the red thing in the next thing is just 1. So it's just, and anything times 1 is itself. So it's just 3x times cos of x minus 2y. And the last thing, now you could be tempted to say, oh, the 3 by 1 multiplies the inside of sine, but that's not really how it works. This is a single number, you can't kind of multiply in. So just in case there might be some kind of confusions, rather than writing sine of x minus 2y by 3, write 3 by sine of x minus 2y. So they'd all be kind of little recommended things to do. All right, so I have another question here. Show that this function satisfies the following. This is called a partial differential equation. They're nasty things to solve. I won't ask you to solve one, but you might be asked to show that something is a solution. So this is like in the matrices, when you want to show things are equal, calculate one side and show that it's equal to the other side. Okay, so now for both of them, we definitely need to do a little chain rule. So I think we're going to calculate each of them separately. So for the first one, and we might just paint in the red constants just we'll keep that going for another little while. So with respect to, what are we differentiating with respect to x? Log of e to the x plus, now with respect to x, that means y is kept constant. And if y is constant, so is e to the y. So that's how we'll view that. And then the other one, we're going to be differentiating with respect to y, log of, now with respect to y, x is a constant. So x is some fixed number, so e to the power of that fixed number is also a constant. So this is how we would see how this is going on. Now both of them, it isn't log of x and it isn't log of y, so we need to do the chain rule. So the chain rule says differentiate the outside. So the outside function here is log of x. The derivative log of x is 1 over x. The chain rule says evaluate at the inside. The inside is e to the x plus e to the y. And then you must multiply by the derivative of what's inside. Now I might just say that when I was younger, I'm probably similar age to a lot of you. The point is, when I was younger anyway, there weren't as many tables. But what was in our tables was the derivative e to the x was e to the x. Now, the reason I'm saying this is actually, that's the real important bit, that the exponential function is, our constant multiples of the exponential function are the unique functions that are their own derivative. Now, that isn't actually in the tables anymore. So what they actually put in the tables now, I think mostly, is e to the constant times x. And while it kind of, you think it helps you for, like, if you want to differentiate e to the 2x, the problem is the one above kind of gets obscured. But make no doubt about it, the e to the x is the unique function that is its own derivative. Okay, so coming back to what we're looking at down here, we've differentiated the outside, we've evaluated at the inside, and now we must multiply by the derivative of what's inside. So we need to differentiate e to the x plus e to the y with respect to x. So the derivative of e to the x, like we just said, is e to the x, but e to the y with respect to x is a constant, so its derivative is 0. And we can tidy that up. So like if I asked you, say, what is that? Now you might say 2 over 3, but that doesn't really mean anything. That describes the symbol. If you're to say this, you would probably say 2/3, and that's exactly what you should think of it, 2 by 1 over 3. Or you could say it's 1/3 by 2, which of course is the same thing because order of multiplication doesn't matter. What I'm getting at is if you've got something multiplied by 1 over something, that's the same as division. So this is actually e to the x divided by e to the x plus e to the y. Now by symmetry, we'd expect to see e to the y over e to the x plus e to the y, but let's do it. So differentiating with respect to y now. So again, you'd expect to differentiate the outside, evaluate at the inside, and then multiply by the derivative of what's inside. And the derivative of e to the x with respect to y, so with respect to y, x is a constant, so e to the x is a constant, derivative of a constant is 0, plus the derivative of e to the y is itself. Or should I say the derivative of e to the y with respect to y is itself. So we end up with e to the y divided by e to the x plus e to the y. And therefore we can add these two together and let's see what we get. So the first derivative with respect to x plus the first derivative with respect to y is e to the x divided by e to the x plus e to the y plus e to the y divided by e to the x plus e to the y. And you've got a common denominator. So take that, e to the x plus e to the y, and you have e to the x plus e to the y, and any number divided by itself is equal to 1, which is what we're supposed to show. So job done. Right, now you can extend it. It doesn't have to be just a function of 2 variables. You can have a function of 3, 4, 5, whatever, as many as you want, in fact. So for example, here we've got a function of x, y, and z. So you've got 3 first derivatives. You've got the derivative of w with respect to x, we'll have a look at that. The derivative of w with respect to y, we'll have a look at that. and the derivative of w with respect to z. Now what we might do is we might do the red thing again. Yeah, we'll keep going. So with respect to x, but y and z are constants. So what we're looking at here when we're differentiating with respect to x is sine of x plus a constant y plus, now x is changing but z and y are kept constant, so you have a constant z squared. Now I've actually missed out on something that I really should have done here. I'll fix it now in a second. E to the x. What I'm missing here is I should be saying that I'm differentiating this. So what I'm trying to say is derivative of w with respect to x is equal to the derivative with respect to x of this. That's better. Similar story, if we're differentiating with respect to y, x and z are constants. So you're looking at sine of x plus, and we'll do all the reds at the end, plus. So with respect to y, made a donkeys of this, of course. X is constant. So what am I trying to say here? So x is a constant, z squared times e to the x is a constant, but y is a variable. And on the last one, we're going to be differentiating with respect to z. So now you got sine of x plus y are both constants. So in fact, the whole shebang here, sine of x plus y is just one big constant. Now you can do the chain rule on it, and what you'll get is cos of x plus y times the derivative with respect to z of x plus y, but the derivative of x and the derivative of y with respect to z are both 0, so you just end up with cos of x plus y by 0, which is 0. And then the z squared times e to the x, with respect to z, the e to the x is a constant. So you understand, you don't have to do this, I'm just trying to help you see how each of the derivatives are different and what's been treated as a constant and what isn't. Okay, so off we go. Now the sine of x plus y, now we could just say, oh, it's cos of x plus y, but like even if it was sine 2x plus y, that wouldn't be the case. So we'll be a bit more careful. We'll use the chain rule. The chain rule says differentiate the outside. Well, the outside function is sine of x. Derivative of sine of x is cos of x. Chain rule says evaluate at the inside. And the chain rule says multiply by the derivative of what's inside. The derivative of x with respect to x is 1, and the derivative of y with respect to x is 0, because it's a constant. Plus, fix the constant z squared, and the derivative of e to the x is itself. Now we could tidy that up. I think we probably have space. So the red thing here is 1, so that's just cos of x plus y plus z squared times e to the x. No problem. Now differentiating with respect to y. So similar story, you're going to have differentiate the outside is cos of x. Evaluate at the inside is x plus y times the derivative of what's inside. The derivative of x with respect to y is 0. The derivative of y with respect to y is 1. And look at that second term with respect to y. Z is a constant, x is a constant, so z squared e to the x is a constant which has derivative 0. So you just have cos of x plus y. And then the last one, well, because x and y are some fixed constant, sine of x plus y is a constant. And then differentiating the other thing, fix the e to the x. And then the derivative of z squared with respect to z is 2z, which you might write perhaps as 2z times e to the x for no particular reason. Okay, so you can, and I think in the next section we might see derivatives with respect to 3 different variables. Okay, so you can also do higher order derivatives, so you can look at second derivatives, third derivatives, but the story is because like there's 2, say, even if, say here, z is a function of x and y, there's 2 first derivatives. If you think about it, there's going to be 4 second derivatives, so we have to be careful. And this is where the notation becomes very important, like you can't just say second derivative, because it could be First with respect to x then y, y then x, y then y. So what we're going to do here is we're going to differentiate z with respect to x and z with respect to y. Okay, so we won't use the red here. So differentiating this with respect to x, so y is a constant. So in the first term, if y is a constant, so a sine of y, so a fixed sine of y, and then the derivative of x with respect to x is 1. Plus, in the second term, y is a constant, times the derivative x squared with respect to x is 2x. And we can tidy that up slightly, sine of y plus 2xy. So that's the first derivative with respect to x. And then you can go back to the start and differentiate with respect to y. So going with respect to y, x is a constant. So in the x sine y, you can fix the constant x, and the derivative of sine of y with respect to y is cos of y. And in the second term, you can fix the constant x squared, and the derivative of y with respect to y is 1. And we can tidy that up slightly, is x cos y plus x squared. Now let's look at the second order, the second derivatives. Okay, so we'll look at this picture in a moment. Well, no, we'll look at it right now. So what we have so far is we have sine y plus 2xy. That's the derivative with respect to x, and we have x cos y plus x squared. Okay. And we can differentiate both of those in two different directions. So you have the original function can differentiate with respect to x or y, and the two first derivatives can both be differentiated with respect to x and with respect to y. Now, the notation is a little bit difficult, but we're going to have some good news at the end. So the first thing is we're going to look at the second derivative with respect to x. So this is written differentiate twice. What are you differentiating? Z, both times with respect to x. And maybe we'll set up all of the notations. The other one is you could do differentiate twice. What are we differentiating? Z, first with respect to x and then with respect to y. Now you might say, oh, shouldn't that be y first and then x? Well, we'll talk about that a little bit later. And then the other one is you could differentiate twice, first with respect to y and then with respect to x. And then you could talk about differentiating twice, both times with respect to y. Okay, now we'll have to just come in clear here and say that this one, first. So the order looks a bit funny, and that's just the way you write f of x. Yeah, so like, say for example, f of x was equal to, say, multiply by 3, and g of x was equal to squaring. Now start with the number, say, 3. So if you want to square first to get 9, and then multiply by 3 to get 27, okay? So what did we do first? We squared, so g first and then f. If you want to write that in the f of x notation, it's f of g of 3. So the g happens first. We actually had a similar thing with the matrices. If you were talking about the matrix AB, B actually acts first. Like if I write A, B, V, B actually acts on V first. So let's just see this. So g is squaring, so it'll be f of 9. And then f of 9 is 3 by 9 is 27. So that's the thing. But if you're a bit confused, there's going to be some good news soon. All right. So let's do these derivatives. So the first one is the second derivative with respect to x. So you differentiate with respect to x, which we've done. That's up here. That's the sine y plus 2xy. And then differentiate that again with respect to x. So just to be clear, we're differentiating this sine y plus 2xy with respect to x. Do I possibly have good space to do something? I'm going to write small and just to be clear. So this means differentiate the derivative with respect to x with respect to x again. And I'll do this for all of them. This one means differentiate with respect to y, the first derivative with respect to x. This one means differentiate with respect to x, the first derivative with respect to y. And this one says differentiate with respect to y and then do it again. So all the kind of video I was talking about the operators and the notation and kind of having a feeling for that these kind of differentiation things are like functions. They take inputs and they produce outputs. They take functions of x and y. They produce as input. They produce functions of x and y as output. So now that I've done that, I don't like look at partial z, partial x, and partial z, partial y. They're up the top of the screen. So let's differentiate sine of y plus 2xy with respect to x. Now y is a constant, so sine of y is a constant. So the derivative of sine of y, if y is a constant, is 0. Then we're going to fix the constant 2y, and then we're going to differentiate x with respect to x as 1. So I just get 2y. Okay, next one over. So we're differentiating the same thing, the sine of y plus 2xy, but with respect to y. The derivative of sine of y with respect to y is cos of y. And we're going to fix the constant 2x. So with respect to y, so y is changing, 2x is a constant, and then the derivative of y with respect to y is 1. So you end up with cos of y plus 2x. Down in the left-hand corner, differentiate first with respect to y, that's up in the top right corner. Now differentiate that with respect to x. So I'm looking at x cos y plus x squared here. I'm differentiating that with respect to x. So with respect to x, y is a constant, so I can fix cos of y. And then the derivative of x with respect to x is 1, plus the derivative of x squared with respect to x is 2x. And I can tidy that up as cos of y plus 2x. And then finally, you can take that derivative with respect to y and differentiate it again. So if you're differentiating the thing in the top right-hand corner with respect to y again, you fix y is changing, but x is constant. So fix the constant x, and the derivative of cos of y with respect to y is minus sine of y. Plus, now, x squared on its own is a constant, the derivative of constant is 0. So that's equal to minus x sine y. So we have these 4 second derivatives. So let's write them down. So this is 2y. This is minus x sine of y. And x first, then y was cos of y plus 2x. And first y and then x was also cos of y plus 2x. So what it means is, if you were confused about the thing up the top of the screen about the order, and if you're confused about why isn't it y first and then x, or vice versa, we've got this symmetry of second derivatives. Now, it actually doesn't always hold. It is possible there's really weird functions where it doesn't hold, but basically anytime you ever see it, they'll match. Now, what I'd like is for, if you were, say, supposed to do differentiate with respect to x and then y, if you and maybe you thought it'd be easier to do y and then x, that you would differentiate with respect to y, then with respect to x, then write down something like this. That would be fantastic. But if you're not really sure and you just kind of differentiate, if you do xy or yx, I'm going to give you the marks, obviously if it's done correctly, because for anything you see, they're going to be the same. Okay, so there's a, why is this true? There's a kind of an explanation of it there. So I think we're going to go at this question here, if there's space. Yeah, so I might need to write down the question for myself. So the function we're looking at is 2x plus xy plus x squared, and we want to show that it solves this partial differential equation. So same as before, calculate the left-hand side and see do you end up with 0. Okay, so first of all, what we could do, and there's different options here, is, now I'm just going to do it as it says it here. So to calculate the second derivative with respect to x. So the first derivative with respect to x. Okay, so it's a sum of terms, so differentiate term by term, fixing constants. The derivative of 2x is 2. Sorry, we're going to fix the 2, and the derivative of x is 1. We'll try and be consistent. Now with respect to x, we're looking at xy. Y is a constant, so fix that, and the derivative of x with respect to x is 1, plus x squared, the derivative of x squared with respect to x is 2x. So I'm seeing 2 plus y plus 2x. And now I have to differentiate that a second time with respect to x. So I'm going to differentiate with respect to x the first derivative with respect to x. So the thing I just calculated, the 2 plus y plus 2x. So let's differentiate 2 plus y plus 2x. 2 is a constant, its derivative is 0. Now with respect to x, where x is changing, but y is kept constant, the derivative of y is 0. And then fix the constant 2, and the derivative of x with respect to x is 1. So the second derivative there is 2. Now we're going to look at the mixed derivative. Now we could say take x and differentiate it with respect to y. So we could take this thing here and differentiate that with respect to y, but we have to calculate the derivative with respect to y anyway, so we may as well go back to the very start and differentiate this object with respect to y. So the mixed derivative, so if you get this the wrong way around, it doesn't really matter, but strictly speaking, it should be, the one in the middle should be y first. So differentiating term by term. Now with respect to y, x is a constant, so 2x is a constant, the derivative of 2x is 0. What am I talking about here? I'm differentiating u. Plus, now I have a constant x times y, so fix the constant x, and the derivative of y with respect to y is 1. Plus the derivative of x squared. Well, with respect to y, x is a constant, so is x squared, so the derivative of x squared is 0. So I get that the derivative of u with respect to y is equal to x, and I think that's one of the things I need. Now let's calculate the mixed one. So the mixed second derivative, differentiate u twice. First with respect to y, which we've done, then with respect to x. So that is the same thing as differentiate first with respect to y, which we've just done, and then with respect to x. So differentiate this thing we just had, the x with respect to x, well, of course you get 1. And now I think we have everything. So we're looking at second derivative plus the mixed partial derivative. I think it's minus 1 over x times the derivative of y minus 2. So this is what we're calculating. So the second derivative, let's go back and see what that was 2. Go on. So that's 2. The mixed derivative is just up there, is plus 1. Minus 1 over x times the derivative with respect to y, that's up the top, that's x, and then minus 2. So I have 2 plus 1, that's equal to 3, that's handy enough. Minus 1 over x times x, now that's basically x divided by x, so it's minus x divided by x minus 1, and we have the minus 2, and 3 minus 1 minus 2 is equal to 0, which did the job. Okay. Now in the next two questions, what you're going to do is you're going to pause the video and try and do it yourself, and then I'm going to do it kind of quickly afterwards. But yeah, so you're going to pause and try this question. Okay. So we're back here. Now I'm going to do this quite quickly because this is supposed to be your effort and struggling with it, and then hopefully when I do it you see where you went wrong. Okay, so we're looking at the derivative with respect to x first of all. So this is treating y as a constant. So when I'm differentiating x cubed y, I'm going to fix the constant y, and the derivative of x cubed is 3x squared. And if y is a constant, so is the derivative, so is y squared. So the derivative of y squared is 0. So I'm going to write that as 3x squared y. Perfectly good. Now I can calculate the mixed derivative, the second derivative. So the second derivative of z with respect to x. Now this next thing I'm writing in, you don't actually have to write this in. I'm just trying to explain what's actually going on here. But just that thing I just wrote, you don't have to write. You can go straight, you can just, if you understand that we're just differentiating 3x squared y with respect to x, that's fine. So we're differentiating that thing anyway, the 3x squared y with respect to x. Everything that isn't x is a constant, in particular 3y, and the derivative of x squared is 2x. And so I end up with 6xy. Okay, happy days. And now we're going to do the mixed second derivative. So this, if you just differentiate the x with respect to y again, I'll give you the marks, but I'd like you to be a little bit better. For example, to understand that different, like you could go back and differentiate with respect to y and then x, but this is, and that's fine. And if that's what you did, happy days. But alternatively, you can use the symmetry of the mixed partial derivatives. So this is to say differentiate with respect to y, the first derivative with respect to x. So look at the 3x squared y, now differentiate that with respect to y. So with respect to y, 3x squared is a constant, and the derivative of y with respect to y is 1. And so you get 3x squared, and fair play if you got that right. Okay, so now we'll do another question. Show that log of x, this is a tough enough question, log of x squared plus y squared, the sum of the second derivatives is equal to 0. So you can pause, there's some hints, and do it yourself. Okay, we're back. So what was the function? Z is equal to log of x squared plus y squared. So we're going to do the first derivative with respect to x. I think we're going to do both of them. Oh no, okay, so derivative of z with respect to x. Now I'll keep doing the color. So it's not as simple, it's not log of x, it's log of a function of x. So we need to use the chain rule. The chain rule says differentiate the outside function. Derivative log of x is 1 over x. The chain rule says evaluate at the inside, that's x squared plus y squared. And then the chain rule says multiply by the derivative of what's inside. And the derivative of x squared plus y squared with respect to x, derivative of x squared is 2x. And with respect to x, y is a constant, so its derivative is 0. So this is equal to 2x divided by x squared plus y squared. Now to differentiate this, we need a quotient rule. And the formula for the quotient rule is on the previous page. So the quotient rule says that the derivative of a fraction, so at this stage I'm not going to write in those things that I said you didn't have to write, we're just going to differentiate that uv thing, is the bottom, this is the quotient rule, times the derivative of the top. So I'm going to differentiate 2x, so I'm going to fix the 2, and the derivative of x with respect to x is 1. Okay, I'm going to need some space over here. Minus the top by the derivative of the bottom. So I need to differentiate the bottom with respect to x. Derivative of x squared is 2x, plus, now with respect to x, y is a constant, so is y squared, so the derivative of y squared is 0. All divided by the bottom squared, and usually you'll never multiply out the bottom. There's no real reasons usually ever to multiply out the bottom. So we can tidy this up. We have x squared plus y squared times 2, so that's 2x squared plus 2y squared. And then the other bit is minus 2x by 2x minus 4x squared. All divided by x squared plus y squared, all squared. Now if there's any ever little questions when you're like, so there's some of you might have tried some kind of a cancellation or something that is just nonsense, but you can take a photo or whatever and send me your work, and you can ask me, oh, why isn't this right? Okay, so what have we got here? 2y squared, 2x squared minus 4x squared is minus 2x squared, all divided by x squared plus y squared, all squared. And I'm saying there's no real simplifications there. So we have to do the same for the second derivative with respect to y. So the first derivative with respect to y follows in a similar manner. So the derivative log of x squared plus y squared, differentiate the outside. Derivative log of x is 1 over x. Evaluate the inside, x squared plus y squared times the derivative of what's inside. Derivative of x squared with respect to y is 0, plus the derivative of y squared with respect to y is 2y. Yeah, and that is equal to 2y divided by x squared plus y squared. And that also needs, if we're differentiating again, this time with respect to y, needs a quotient rule. But just remember, we're differentiating with respect to y. So x is a constant. So we differentiate it. Have I made a donkeys? No. Differentiate again. Very tired actually. I could make a donkeys of it at any point. So it's the top. Now, if you're kind of smart, you maybe see by symmetry, it's going to have to be 2x squared minus 2y squared, but we won't ruin the surprise. So I might have said the top. It's the bottom by the derivative of the top. So fix the 2. What's the derivative of y with respect to y? 1. Minus the top by the derivative of the bottom. And it's the derivative of the bottom with respect to y. Now, with respect to y, x is a constant. So is x squared. And the derivative of a constant x squared is 0. Plus the derivative of y squared with respect to y is 2y. All divided by x squared plus y squared, all squared. And we'll tidy this up a little bit. We'll take our time. So the x squared plus y squared times 2 is 2x squared plus 2y squared. And then minus 2y by 2y is minus 4y squared. All divided by x squared plus y squared, all squared. And so we have 2x squared, and then 2y squared minus 4y squared is minus 2y squared. Okay, so now what we can do is think, what was the actual question about? Oh yeah, show that the sum of the second derivatives is 0. So what have we got? The second derivative with respect to x plus the second derivative with respect to y is equal to, so we're adding these two yolks on the right hand side. They have a common denominator. Look, I'll go a bit slowly, there's no harm. Well, I'll write it quickly. So they have a common denominator, so we can add them together quite easily. So we end up with common denominator, I find that hard to say. And then what have we got? 2y squared minus 2x squared plus 2x squared minus 2y squared. And if you look on top, you have 2y squared minus 2y squared is 0. You have 2x squared minus 2x squared is 0. So you have 0 divided by something, but 0 divided by anything is 0. And that's what we're supposed to show. Okay, that's a long enough lecture there.